So in the last video, you learned how to do mass-to-mass conversions with stoichiometry. Those were problems where you were given a mass, needed to convert to moles, and then solve for a mass. However, we can also do stoichiometry with volumes and with particles. That is to say, with milliliters or liters, or the number of molecules. Do a couple of examples of that here. Question 1 reads, what volume of HCl forms when 56 milliliters of POCl3 completely react according to the reaction below? And you're given a couple of densities. So just like before, I want to walk us through visually what we can do and then set up a few fractions to show the math. Let's start with what we're given. We're given 56 milliliters of POCl3. I ultimately want to figure out a volume of HCl. However, I need to use a mole-to-mole ratio to tell me the moles of HCl formed for every mole of POCl3 consumed. To do that, I need to solve for moles. So let's first use a density to convert milliliters into grams. The density of POCl3 is 1.67 grams per milliliter. Then let's use a molar mass to convert grams of POCl3 into moles. The molar mass of POCl3 is 153.32 grams per mole. At this point, I can use my mole-to-mole ratio, which would be 3 moles of HCl that form for every 1 mole of POCl3 that's consumed. That calculation will solve for moles of HCl. At that point, I can use the molar mass of HCl, which is 36.46 grams per mole, to solve for grams of HCl, and then use the density of HCl, or 1.49 grams per milliliter, to solve for milliliters of HCl. Again, visually, what we're looking at is a conversion from milliliters to grams to moles, mole-to-mole ratio to grams to milliliters. And that will tell us the milliliters of HCl formed when 56 milliliters of POCl3 react. To write that out mathematically, we would again start with 56 milliliters, put it over 1, multiply by 1.67 grams per milliliter. That's this step right here. Multiply by 1 mole over 153.32 grams. That's this step right there. Multiply by 3 moles of HCl per 1 mole POCl3. That's this step right here. Multiply by 36.46 grams per mole of HCl. And finally, multiply by 1 milliliter per 1.49 grams. Checking our units. Everything cancels out. We go through and solve and come up with 44.78 milliliters, which, if we need to convert to 2 sig figs, would work out to 45 milliliters. Again, same idea as the mass-to-mass problems. However, we're adding in the extra step of now needing to convert from a volume to a mass. And at the end, also converting from a mass to a volume. Consider another equation. This is C5H12, which is pentane, decomposing to C5H8 and 2 H2s. Pentane decomposing to pentyne and hydrogen gas. The question reads, how many liters of H2 can form when 4.53 times 10 to the 3 milliliters of C5H8 form? Question 3 reads, how many milliliters of C5H12 are needed to make 97.3 milliliters of C5H8? So we have two different problems going on here, but they're both going to follow the same pattern. I want to visually walk us through again To do that, we can write the equation for this decomposition. As before, let's start with what we're given. 4.53 times 10 to the third milliliters of C5H8. The question here reads, how many liters of H2 form when that amount of pentyne also forms? So, just like we did before, let's use a density to convert those milliliters into grams, a molar mass to convert those grams into moles, a mole-to-mole ratio, a molar mass to convert moles into grams, and finally a density to convert grams into milliliters. I'll leave it up to you to solve that problem. Likewise, I'll leave it up to you to solve the second problem, which is related, uses the same equation, just asking you to solve for different things given different information. In addition to volume problems, we can also solve for particle problems, where we're given the number of molecules, atoms, or formula units, and asked to solve for something else. In this case, in question 4, the question reads, how many grams of C5H8 form from 1.89 times 10 to the 24 molecules of C5H12? You notice it's the same equation as before. Let's start with what we're given. 1.89 times 10 to the 24 molecules. With a number of this size, it's an immediate clue that you should use Avogadro's number to convert. It's just what we'll do here. We can multiply this number by Avogadro's number by 6.022 times 10 to the 23rd molecules per mole, and that will convert our molecules into moles. I can do a mole-to-mole ratio, and then the question asks to solve for grams. So just like what we started with, we can use a molar mass of C5H8 to convert moles of C5H8 to grams of C5H8. In this case, the molar mass is 68.13 grams per mole. To give you an idea of what that would look like mathematically, let's write out the fractions. We start with 1.89 times 10 to the 24 molecules of C5H12. We can multiply that by 1 mole over 6.022 times 10 to the 23rd molecules. Specifically, that's 1 mole of C5H12. Then we can use our mole-to-mole ratio, which we see is 1 to 1, that we're generating 1 mole of C5H8 for every 1 mole of C5H12 consumed. And as our last step, we'll multiply by the molar mass, by 68.13 grams for every 1 mole of C5H8. We started with molecules. Sorry about that. Started with molecules, converted to moles, did a mole-to-mole ratio to figure out the moles of product formed, and then used a molar mass to convert to grams. In this case, we would get 213.8 grams, or because we were given just 3 sig figs, 214 grams of C5H8 that form. One last example. The question here reads, how many molecules of carbon dioxide form from the complete combustion of 3.25 times 10 to the 24 molecules of C6H6? C6H6 is a compound called benzene, which is actually pretty interesting and pops up quite a bit in chemistry. We'll come back to it later in the course, but you maybe recognize some of these shapes or some of these shapes from either biology or other science courses. AP Chemistry will talk about delocalized pi bonds and hybridized orbitals. Back to the question. We're combusting 3.25 times 10 to the 24 molecules of benzene. As has been the case all along, we need to get to moles so we can do a mole-to-mole ratio. Just like the above problem, let's use Avogadro's number to convert molecules to moles. Let's do a mole-to-mole ratio. Now the question reads how many molecules of CO2. So let's use Avogadro's number to go back to molecules. If we set this problem up, start with what we're given, 3.25 times 10 to the 24 molecules of benzene. Using Avogadro's number, we can say that there's 1 mole of benzene for every 6.022 times 10 to the 23rd molecules. Once we know the moles of benzene we know that 12 moles of CO2 are produced for every 2 moles of benzene that are consumed. There's our mole-to-mole ratio. And finally, we can use Avogadro's number again to convert to molecules of carbon dioxide that are produced. That'll be 6.022 times 10 to the 23rd molecules for every 1 mole of CO2. Now if you go to punch this into your calculator, you can see that 6.022 times 10 to the 23rd appears in both the numerator and the denominator, so you can ignore it from your calculator, which might save you a few keystrokes. Doing this math out, we should get 1.95 times 10 to the 25th molecules of CO2. Two final problems, both involving molecules, that I think would be extra practice and helpful for you to check your understanding of the work here. At the bottom, after you've taken some time to work through these problems and work through the ones above that we left blank, there's an answer key right here. Check your answers and see if you agree. Thanks for watching.